Hello everyone and welcome back to the online physics lessons. Alright, in this video number 3 we're going to discuss the difference between the gravitational force and the electrostatic force, in particular Coulomb's law. So before we begin, we're going to take a look at the reference table and notice that on page 4 you have several formulas under electricity. Several formulas. And electricity starts with E1, the Coulomb's law, and then you have electric field strength, and you have electric potential, which we'll be doing a separate video on that. And these three formulas are what are found in the electrostatics unit. After that, the other formulas and everything below it, that is for current flow and electrical circuits. So we're going to be focusing right now on this formula. Fe equals kq1 q2 over r squared. So we already know this formula in its gravitational form, and as you can see, the gravitational form was gm1 m2 over r squared. The strength of attraction between two masses was determined by the magnitude of the masses divided by the distance between them squared. And of course that's multiplied by the universal gravitational constant G. Big G, capital G, which, to remind you, was on the reference table on the first page, right here at the top, G. We're going to be using the electrostatic constant K right here on the first page of the reference table, about halfway down, formula number 11. The idea that two masses can be attracted to each other based on their proximity is mirrored in the electrical world, that two charges can be either attractive or repulsive depending on their signs, and we use the law of signs. Two charges are attracted if they have opposite signs, and they are repelled from each other if they have the same sign. So two positives or two negatives is a repulsive force, and a positive and a negative is an attractive force. Gravitation was only attractive, whereas electrostatic force, the Coulomb force, can be either attractive or repulsive. When we used the reference table for the universal gravitational constant G, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, first page of the reference table, we have an equivalent electrical constant, electrostatic constant, 8.99 10 to the 9th Newton meter squared per Coulomb squared. Since we're dealing with charge, charge is measured in coulombs. Now, a little something to point out about the units. These two constants have almost identical units. The top is Newton meter squared for both. The bottom here for gravitation is kilograms squared. The bottom here for electrostatics is Coulomb squared. When you're dealing with a mass, you're going to be dealing with kilograms. When you're dealing with a charge, you're going to be dealing with coulombs. We are now going to practice an electrostatic force problem using the Coulomb's law. Here we have a Coulomb's law example. Base your answers to the question on the information in the diagram below. Two small metallic spheres A and B are separated by a distance of 4 times 10 to the negative 1 meters, as shown. The charge on each sphere is a microcoulomb. Now, the Regents often uses scientific notation for numbers like 0.4 meters, just to see if you recall how to use the scientific notation. The first question that's asked is to calculate the electrostatic force between the two spheres. We set up the equation as follows. Kq1 Q2 over r squared is the Coulomb formula that we found on the reference table right here. Q1 and Q2 are the two charges that you're going to have to input. Those were given as 1 microcoulomb each. And of course the K comes right from the reference table, and the distance, 4 times 10 to the negative 1 meters, all of that has to be squared. So let's just take a look right now at this little 10 to the negative 6, and the problem gave us 10 to the negative 6. That's a micro Coulomb. Micro. On the front page of the reference table, there's a chart at the bottom left corner of the reference table that reminds us that 10 to the negative 6 is a micro. Sometimes the problem is given as micro Coulomb. Sometimes they write it out longhand. What is particularly concerning for many students is how to properly input the data of scientific notation into a scientific calculator. So I have a setup over here in this red brackets showing the precise key punch entry. There are other methods that students use that I've warned that can cause keystroke errors, so let's try to be efficient in the way we use it. So 8.99 times 10 to the 9th, there's your scientific notation, multiplied by, and now you have 1 10 to the negative 6 times 1 10 to the negative 6, close your parenthesis, divided by 4 10 to the negative 1, and hit the x squared button. This is very important because when you get this order of operations correct, it'll return a result 5.6 10 to the negative 2 newtons. And since it is a positive value, and they're both positive charges, it's repulsion. The next question that could be asked is to calculate the electrostatic force between the two spheres when the distance between them is doubled. Alright, so common trick of the regions is to double distances, halve distances, triple them, take a third, and to see if you recognize the 1 over r squared relationship. So 1 over r squared, if you double a distance down here, 2 squared is a fourth. There's 1 over 4. So it's 1/4 of the original distance. And what if we halve the distance? So 1/2 is now at the bottom of this equation. 1/2 squared is 1 over 1/4. Invert that and you get quadruple. 1 over rule works with this curve right here. 1 over r squared. So if you double a distance, you're getting further away. You're getting a weaker force of attraction or repulsion. In this case, it was repulsion. And if you bring it closer, bring the two charges closer together, you increase the attraction or the repulsion by 1 over r squared. Okay, in the last part of this video, we're just going to take a closer look at properly entering the Coulomb formula into your scientific calculator. So here I have a picture of a TI-84 Plus, which is what most of you are using. And here's a picture of the keypad as well. This was taken at my desk with the overhead camera. The most important thing that you see is a comparison of what I've actually written in this area right here, the keystroke entry, versus what you actually see on your computer. So here it is. 8.99, second function, comma, there's your comma right here. That gives you your capital E. That means times 10 to the, and then you put your 9 for 9th power. And then you put the asterisk, which is your multiplication button found over here with all your addition, subtraction, multiplication, division symbols. So you pick that. And then you have 1 E, so it's second comma, times 10 to the negative 6. Be careful when you're picking negatives, you don't choose the minus sign by accident. Minus is over here. Negative is right here. That's a -1. So that's another place students can make an error. And then this arrow, this triangle right here, shows that there's a little more of the formula right there. It's the rest of the formula being divided out. But if you can get these first figures entered in correctly, you just repeat the process for all the numbers that you see in the longhand math. And when you hit enter, 056, and it's a positive value, which means repulsion. All right, that's the basic setup for a Coulomb's law example. Another thing you might want to note is that they can ask you to draw the electric field between the two charges. Since these are both positive, 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 it goes like this. It's that dancing starfish we talked about. Each field would come up and move away. You now have a complete explanation on how to calculate the electrostatic force between two charges. We'll see you in the next video.